Hello and welcome to this second lecture in this course on atomic and molecular structure and spectroscopy. So in last lecture we looked at the hydrogen atom and the electronic states available for a hydrogen atom and some of the transitions between them. Today we're going to move on and look at other atoms, so atoms with more than one electron. You'll be familiar for a long time with the Aufbau principle, so which are the three basic rules for putting electrons into orbitals. The first of these is the Pauli exclusion principle, which states simply that no two electrons can have the same set of quantum numbers NL, ML and MS. Second one we tend to do naturally, so we put electrons into orbitals with the lowest energy available. So if you've got just an empty atom, we don't put the electron into the 3D orbital, we put it into the 1s orbital and we fill up from the lowest energy. Last one is Hund's principle, and this is that electrons tend to occupy degenerate orbitals singly with parallel spins before they then start pairing up. And this becomes important when you start filling up, for example, the p orbitals or the d orbitals, but you should be very familiar with this by now. So using the Aufbau principle, we can actually write down the electronic configuration for any given atom, and we can then start thinking about the electronic states available to this atom. So first of all, we can ignore closed shells. The reason for this is that first of all, everything sort of cancels out and just doesn't count towards the overall angular momentum of the system. So if we've got a spin up and a spin down electron, the overall spin is 0. If we've got full electrons in orbitals with ML equals 1, 0 and -1, well, the overall spin is 0. The overall orbital angular momentum is 0 because they sum to 0. So we then have two types of atoms. So we have hydrogen-like species, so things with one electron in the valence shell, and we have other atoms, so basically everything else. So let's deal with hydrogen-like atoms first. So basically these can be dealt with in exactly the same way that we dealt with hydrogen in the last lecture. So an example would be lithium. So here's three possible electronic states for lithium. We have the ground state of lithium, or there's two excited states here. In each of these, you'll remember I've said that if you've got a closed shell, we can ignore it. So we can cross out, effectively ignore the 1s orbital with the two electrons in it, and this leaves us with one electron in the 2s orbital, in the 2p or the 3d, which we can deal with based on what we did last week. So that's nice and easy. So we end up with various terms, and you remember I mentioned the splitting was small for hydrogen between various states. This gets larger when you increase the atomic number. So it's about 0.3 wave numbers for hydrogen. It's getting on for a wave number for lithium, 17 wave numbers for sodium, and then 5,000 wave numbers for cesium. But they're very simple to treat in order to get the states. I should say that this approach, which we've used for hydrogen, also works for electron holes. So for example, we have fluorine here, so we can ignore the 1s2s, we can ignore the 2s2 electrons because that's a full subshell. We're left here with 5 electrons in the 2p orbital. Well, this actually corresponds to having one electron hole in the 2p orbital. So instead of doing the calculations on 5 electrons, we can just do it on 1 in its equivalent. So this gives us an easy way to work out electronic states for almost full orbitals. If we now move on to other atoms, it gets a little bit more complicated because we need to start considering the coupling between the various electrons in the incompletely full orbital. So we need to ask ourselves, well, how do we do this? Which order do we couple them in? and does this affect what the answer you get is. And there are basically two main approaches for doing coupling between electrons in orbitals. The first one is called JJ coupling, and this is typically used for heavy atoms. And I'm going to mention it briefly, but we're not really going to apply this approach in this course. The other approach is called Russell-Saunders coupling. This is also sometimes called LS coupling. And this approach is used for light atoms. Now, when I've said light and heavy, I haven't said what a definition of a light or heavy atom is. Basically, there's some point at which JJ coupling starts to give better results than the Russell-Saunders coupling. But in general, for top of the periodic table, we'd use the Russell-Saunders coupling. And that's the coupling approach we're going to look at in a bit more detail. First, let's think about JJ coupling, just so you're aware of what it is and how it works, and then you'll see the differences when you go on to look at the Russell-Saunders coupling. So we've got our electrons in an open shell, in an incomplete shell. The electrons will be in orbitals with different L, and they'll have different ML. They'll have different S values depending or MS values depending whether they're spin up, spin down, and so on. So we need to what we do in JJ coupling is to couple the individual momenta for the individual electrons separately. So we'd couple L1 and S1, so the orbital angular momentum and the spin angular momentum for electron 1 to give us our total angular momentum for electron 1, and then we do the same for electron 2, and so on. We then couple these J values to give the overall angular momentum, capital J. So you can see why this is called JJ coupling, because we're working out the individual J values and then coupling those to give our final value of J. If we have two electrons, if we have J1 is larger or equal to J2, the final values that capital J can take are given in this list here. So basically it's from the sum of the two J values down to the difference between the two J values. All these numbers are going to be positive. The last value could potentially be equal to 0 if J1 is the same as J2. Otherwise it's going to be a positive number. It doesn't have to be integer, as we've seen. So it'll either be integer or half integer. So that's JJ coupling. I'm not going to talk about that any further. What I am going to talk about in a bit more is Russell-Saunders coupling, so the LS coupling. And in this coupling scheme, what we do is we couple the orbital angular momenta L for all of the electrons to give our total orbital angular momentum, capital L. Then we can do the same with the spin angular momenta, little s, which we couple together to give the total spin angular momentum, capital S. So it gives us our capital S value. And then what we do is couple our L and S, capital L and capital S together to give our capital J, so the total angular momentum for the atom. So you can see why this Russell-Saunders coupling is also known as LS coupling, because this is what we couple together at the end. Okay, we now need to actually work out how to calculate, how to couple these angular momenta together. So let's take a simple case. We'll just look at two electrons, because if you can do it for two, then you can then effectively do it for more electrons as well. So you've got two values of L, so your orbital quantum number. We'll take the largest one, call it L1, and we'll call the other one L2. We can then calculate the sum and the difference of these two numbers, and basically capital L can then take all values in between these two extrema in steps of 1. So we know that L is always going to be an integer number, because L takes the value of 0, 1, 2, and so on, up to n minus 1. So all these L values are going to be integer numbers in steps of 1. We can then do the same for calculating the spin, the total spin angular momentum. So we take the largest value of S and call it S1, and the smallest value of S and call that S2. If we're dealing with electrons, S is always going to be plus 1/2, so S1 and S2 are going to be the same. What we then do is calculate the sum and the difference between them, and then in exactly the same way we say that capital S takes values between the sum and the difference of these two values with integer steps between them. Now we've got our capital L and capital S, so we now need to couple those together, and surprise surprise, we do this in exactly the same way. So if L is greater than S, then J can take values between the sum and the difference of these numbers. If S is greater than L, you just do it the other way around, and you get numbers between S plus L and S minus L. All this does here is it avoids us getting negative numbers, because these numbers are always going to be greater or equal to 0 here. They can't be negative. So if L is actually equal to S, we can use either of these, and of course the last term will be 0. Okay, so that's all very well in theory. Let's do a worked example. So I'm going to take a simple case. Let's take the helium atom, but I'm not going to take the ground state of helium. I'm going to take an excited state of helium, so I'm going to denote it with an asterisk. And let's put it in the electronic configuration 1s1, 2s1. So you can see we've excited one electron from the 1s orbital into the 2s orbital. So now you'll remember that we need to work out our various values. So let's have a look at L first. So we need to work out L1. So electron 1 is in a 1s orbital, and that has an L of 0. Then you can work out L2. Electron 2 is also in a 2s orbital, which has an L of equals 0, so L2 is equal to 0. So we can, going through what I showed you just before, we can say the capital L is equal to 0. And this basically means that we've got an S state. So that's what's going to go into our term symbol. Let's now think about S. So S1 is plus 1/2 because it's an electron. S2 is plus 1/2 as well. So we have two ways of combining these. We can either add them together or subtract them. So this gives us two values of S. So S can either equal 1, which is S1 plus S2, or it can equal to 0. So this is S1 minus S2. Now we need to work out J values. In this case here, we have that S is greater than L, so you can use the this means that J takes the values between S plus L down to S minus L. So if we take S equals 1 and L equals 0, this gives us J is equal to 1. Okay? And if we take an S minus L, well, that's also gives us J equals 1. 1 minus 0. Yep. If we now take the other one, so S is 0, 0, plus 0. This gives us a J equals 0. Okay, so now we've actually got all the things we need in order to just write down the term symbol. So the term symbol is 2s plus 1 L subscript capital J. So if we have the state where s is equal to 1, 2s plus 1, 2 times 1 plus 1 is equal to 3. So this gives us 3. L is equal to 0, so it's an S state. J equals 1. So we now have a triplet S1 state. And the other one is going to be the state where S equals 0. So if S is equal to 0, 2s plus 1, the multiplicity is equal to 1. So that gives us a singlet state. L is equal to 0, so that gives the S state as we've seen before, and the J is equal to 0. So for the excited state of helium with 1 electron in the 1s orbital and 1 electron in the 2s orbital, it gives us 2 electronic states, a triplet S1 and a singlet S0 state. So it's as simple as that. You'll have seen in this example we had 1 electron in the 1s orbital and 1 electron in the 2s orbital. This means we can actually, the electrons are different, and this makes the coupling easy. If you have equivalent electrons, so that's what I just said, it gets a bit more equivalent if a bit more complicated if you have equivalent electrons, say for example in a carbon atom. So here we have 2 electrons in our 2p orbital, but these are equivalent, so they can be, we don't know exactly which orbitals they're in. All we know is that they're going to be parallel in the ground state. And same for nitrogen. If we have 3 electrons in the 2p orbital, we can put them in, but we don't know exactly where they're going to be. And they're all actually the same because they're all in a 2p orbital. So this is what we're actually going to do in the classroom session. It's a bit more complicated, so we'll work through it in class. Okay, so now we've got these various electronic states for an atom. We need to know in which order they come, because associated with these states they'll have a specific energy. So we need to know which ones are higher or lower in energy, and this is where Hund's rules come in. So if we have a given electronic configuration, say we have 2 electrons in the 1s orbital and one electron in the 2s orbital, so ground state of lithium, we will work out the available states. Hund's rule number 1 says that the state of highest multiplicity is always lowest in energy. So this means that if you have a triplet state and a singlet state, well, the triplet state has higher multiplicity, so it's going to be lower in energy. If we have within a state within states of a given multiplicity, the state with the highest value of L lies lowest in energy. So if we have a triplet P and a triplet S, the P state has an L of 1, whereas the S state has an L of 0, so the triplet P will be lower in energy than the triplet S. And finally, for a given value of L, we then have a choice. So if the shell is less than half filled, so if it's like carbon in the ground state when you've got 2 electrons in the p orbital, then the component with the lowest J value lies lowest in energy, whereas it's the other way around if the orbital is more than half filled. Let's now again see an example of how we do this. So again, let's look at helium. So the low energy states of helium, so we can have helium in the ground state. This gives us a singlet S0 state. We can have an excited state of helium. So this is what we just did before. So we get a singlet S0 state and we get a triplet S1 state. If we now have a 1s1, 2p1 configuration of helium, this gives us more states. So we have singlet p1, we have a triplet p0, we have a triplet p1 and a triplet p2. So you could actually work all these out for yourself, be a good useful practice for you. So we now need to put these into order. So Hund's rules basically say that for a given electronic configuration we can then apply the rules. But here we've got 3 different electronic configurations, so we've got to use our chemical knowledge. So we know that a 1s orbital is lower in energy than a 2s, which is lower in energy than a 2p for atoms beyond hydrogen. So we know that these ones here are the lowest. Well, this is going to be the lowest energy state. These are going to be next, and these ones are going to be the highest. So we can already do that. So what I can do is, if I start building up an energy diagram down here, I can already put in our one singlet S0 state down here. Now we know these 2 states here come next. We've got to put them in order. So if we apply Hund's rule number 1, it says that states with higher multiplicity are lower in energy than ones with lower multiplicity. So this means a triplet state will come before a singlet state. Whoop. So next here we'll have our triplet S1 state, and then next will come our singlet S0. I'm not drawing this to scale, I'm just putting them in order at the moment. So we've done the first 3 states, we've got these next 4 states to think about now, so these ones here. So Hund's rule number 1 again says that triplets come before singlets. So we know that these 3 states here are going to come before the singlet P. So what I'm going to do is I'm going to put these 3 here, and I know this is going to be the singlet P1 state. Now we've got these 3 triplet states. We've now got to decide which of these come in which order. So we're in the p orbital. We know that we've only got 1 electron in the p orbital, so the electron shell is less than half full. So this means that the ones with the lowest J value are lowest in energy. So these 3 states here are going to be a triplet P ones, and then the J values here are going to be 0, 1 and 2. So this bottom one here is the triplet P0, then we have the triplet P1 and the triplet P2. Okay, so we've now used Hund's rule to put these electronic states in order of energy. Now we've got these electronic states, we need to think about whether transitions are allowed between these states. So we need to know the selection rules. So when we have several electrons, we can't work with the little letters anymore, we need to work with the capital letters. So we need to work with the total spin angular momentum, and the change in this value. So delta S has to be equal to 0 for light atoms. So this does actually break down when you get further down the periodic table, but for our purposes we'll assume that delta S is equal to 0. For the orbital angular momentum component, we have delta L can equal 0 or plus and minus 1. But then we actually have the additional restrictions that delta little l has to be plus or minus 1, and additionally that we can't have transitions going from L equals 0 to L equals 0. So we don't have S to S transitions. Finally, there's a selection rule for the total angular momentum, so delta J, so capital J, has to equal 0 or plus or minus 1. Let's now again put this into practice in a worked example. So what we're going to do is go straight back to our helium example from before. So we built up our energy level diagram. So we had 1s2, a singlet S0 state down at the bottom. The next state was a 1s1, 2s1, and this is a triplet S1 state. And then we had 1s1, 2s1, and this is our singlet S0 state. I'll just put that over here. It looks simple. Keep it tidy. Then we've got our 1s1, 2p1 states. So these are the triplet p1s with j equals 0, 1 and 2. And last with this is our 1s1, 2p1 state, giving us a 1p1 term symbol. So now we need to think between which states can we have transitions. So let's just work from the bottom up. So if you go from the 1s state, singlet S, are we allowed to transition to the triplet S state? The answer is no, this is forbidden for spin reasons. Can we go from 1s singlet S0 to the singlet S0? Well, the spin bit is allowed, but you'll see that we've got an S to an S transition, so this actually isn't allowed. This is the delta little l is equal to 0, whereas we've seen from the selection rules that delta little l has to be plus or minus 1, so that's also forbidden. Can we go from the singlet S up to the triplet P? Well, no, we can't, because we can't go from a singlet to a triplet. That's not allowed. Are we allowed to go from a singlet S0 to a singlet P1 state? Well, the spin's multiplicity stays the same. Capital L goes up by 1, that's allowed, and capital J goes up by 1, so that's allowed. So this transition is an allowed transition. But that's the only transition which is allowed, well, amongst these states, from this ground state here. Let's take the next state up. So triplet S1, where can we go from here? Can we go to the singlet S0? No, we can't, because it's a change in multiplicity and that's not allowed. Can we go from triplet S1 to a triplet P? Yes, we can. We need to look a bit more closely. So triplet S1, if we go to the triplet P0, then delta capital L is plus 1 and delta capital J is minus 1, but that's allowed, so this transition is allowed. Triplet S1 to triplet P1, so the spin's fine, the delta capital L is plus 1, so that's fine, and delta J is equal to 0, so that's also allowed, so this transition here is also allowed. Triplet S1 to triplet P2, spin's fine, delta capital L is plus 1, which is fine, and delta capital J is plus 1, which is also fine, so this transition is also allowed here. How about triplet S1 to singlet P? No, that's not allowed, that's spin forbidden. Let's take the next one. So singlet S0, can we go to triplet state? No, we can't, because that's spin forbidden. Can we go from singlet S1 to singlet P1? So spin's fine, delta capital L is plus 1, which is fine, delta capital J is plus 1, which is also fine, so this transition here is also allowed. Let's look now at these transitions here. Can we go from triplet P0 to triplet P1? Well, spin's okay, the delta capital L is 0, which is also okay, but we're staying in a p orbital, so we're going delta little l is 0, so this transition is not allowed. The same from the 0 to 2 and the same from the 1 to 2, so they're all forbidden. Can we go from any of these triplet P states to the singlet P states, or singlet P state, sorry? Well, no, we can't, because it's spin forbidden, because we can't go from a triplet to a singlet state. So by considering the selection rules and these low energy states of helium, we've worked out which transitions are allowed and which ones aren't. So you'll get lots of practice at calculating these tone symbols and the transitions in the classroom session. As time is a bit tight before the next lecture, there's no homework or pre-classroom task associated with this lecture, but come along ready to put it all into practice. And that brings me to the end of lecture 2.